Hello guys, welcome you all to this video. Here we are going to start this video with the definition of uncountable set. Uncountable set. As the name suggests that the set is not countable. So basically the set is neither finite nor denumerable. Okay, so the moral of the story is numbering is not possible. That is, 1 to correspondence with the set of natural number is not possible for uncountable set. I am giving you some standard example like R, C. Okay, these are uncountable set. And then set of all irrational numbers. These are all uncountable sets. Like in the previous video, we have shown that Q is countable. Q is countable. Q means the set of all rational numbers. So R minus Q, that is Q complement, which turns out to be uncountable. Okay, fine. With this you can say brief introduction to uncountable set, we are moving on to some you can say little definitions like interval, okay, then infinite cardinal number, and then we have Cantors Continuum hypothesis. So all these things we will be discussing, and then we will moving on to some questions which will give us actual flavor of this chapter. Okay, so the thing is interval. Now interval, we usually use this term interval, and randomly we use the interval notation. But what is the definition of interval? The main idea behind interval is like, suppose E is a subset of your real line. Okay, now let or consider xy belongs to this E. Fine, that is your minus infinity and it is your plus infinity. So you have this real line and you have said this is your E. Fine, and x, this is y. You have taken xy belongs to E, and suppose x less than z less than y. This is your hypothesis. These two are your hypothesis. That immediately implies, if this implies z belongs to E, that is in between there is some z and that z belongs to E, then we say our E is nothing but an interval. Fine. This is the, you can say, more sophisticated definition of an interval. We have actually 11 types of interval in our hand. Like usually we use open interval AB or closed interval AB, obviously A less than B. This type of things we randomly use. Like open interval AB means A, B, endpoints are not included. Closed interval means endpoints are included along with the points in between this zone. Okay, and parallelly we have semi-open intervals like this way, and if we include minus, then we have this sort of thing, minus infinity. Okay, A comma plus infinity and closed interval A comma infinity, these are there. In fact, we have minus infinity plus infinity. This is another interval, and this interval is nothing but our whole real line. And also we have, suppose phi is there, phi we can simply write it like open interval A comma A, and a singleton set, suppose A, we can write it like A comma A closed interval. Okay, so we have 1 2 3 4 5 6 7 8 9 10 11 types of standard intervals in our hand. This will come again and again in our subsequent videos and problems. So introduce yourself with these intervals. Okay, fine. Now with this understanding or basic information, we are moving on to infinite cardinal number. That is another very important section of this chapter, that is infinite cardinal number. Infinite cardinal number. Already you are aware of cardinal number, that is number of elements of a set, that is nothing but the cardinality of that set or the cardinal number of that set. Okay, that idea is there, but here we have introduced some notions, or you can say notations, like alif naught. This is alif naught, a Hebrew letter, alif naught, small c. These are there to represent infinite cardinal number. So cardinality, take it as your note. Cardinality, it is n if set A is finite set with number of elements equals to n. Okay, cardinality is alif naught if this A is equivalent with set of natural number. This cardinality is small c if A is equivalent with R. In other words, A is equivalent with n means A is nothing but countable set. Okay, if A is not finite but A is countable, in that scenario you have the cardinality alif naught as the cardinality of A. And if A is equivalent with R means A is uncountable set. In that case, the cardinality of A is C. This idea or notations will come again and again in our subsequent parts. Fine. So, if you simply try to understand the facts by a diagram, then we have R. From R we have two cases. A subset of R, it may be finite, it may be infinite. Okay, if it is finite, then straightforward it is countable. If it is infinite, then still it has two subcases. One, that infinite set may be denumerable. Okay, that means onto-ness can be generated, that is numbering can be generated. That means that is your denumerable set. And other one is uncountable. Okay, that is that set is not denumerable. Fine. For example, here is the set of all irrational number. Here is the set of all rational number. So the cardinality of that denumerable set is nothing but alif naught. And here the cardinality is going to be small c. Correct? Okay. So this is the whole scenario. That means if you have a set, suppose S is a subset of R. S is a subset of R. Immediately that implies either S is equivalent with N or S is equivalent with R. If S is equivalent with N, then you have alif naught as your cardinality, and if it is equivalent with R, then C is your cardinality if the set is not finite. Okay. So here this S is obviously infinite set. So you have these two understanding. This is one by this chart or by this way. Okay, fine. Now as you know that two sets, suppose you have two sets with the same cardinality. This fact we have already discussed in our, I think, last or that previous video, that if, take this as your note, if two sets have same cardinality, that is, or the two sets have same cardinality if and only if they are equivalent. Okay, likewise you have Z, it is equivalent with N, so the cardinality of Z, it turns out to be L if naught, correct? And Q, it is equivalent with N, so cardinality of Q, it is going to be L if naught. So the cardinality of Z and cardinality of Q are same. By that statement you can say Z is equivalent with Q. It's the set of all integers. Okay, it is equivalent with set of all rationals. Fine. All right, now we are moving on to Cantor's hypothesis, and then we will deal some question. Okay, after that in the subsequent video we will start rest of the part, that is you can say algebra related to this cardinality. Okay, cardinal arithmetic, basically that's the thing. Okay, now the Cantor's hypothesis, Cantor's Continuum hypothesis. It is, you can say, it is one of the most famous unsolved mathematical problem. That is the statement, first of all I am writing it, there is no infinite cardinal number, there is no infinite cardinal number between L if naught and C. Okay, there is no infinite cardinal number between L if naught and C. In fact this statement till today's date there is no proof regarding this statement and no counter example regarding this one as well. So it is you can say conjecture type of statement, which is one of the, you can say, very beautiful and famous hypothesis of mathematical world. Fine, I have just mentioned this continuum hypothesis because it will come in the subsequent video. Fine, now another diagram, just giving you just for your understanding purpose. Suppose any subset of R, it has three possibilities from cardinality's point of view, that is either it is finite, or it is L if naught, or it is C. One of these three has to happen. That is the moral of the story. Fine, with all these things in our hand, now we are in a position to tackle our first question of this topic. I am giving you this question and let me know in the comment section what is your answer, and in the upcoming video I will give you the solution. So the first question just in the comment section just mention what is going to be your answer, and maybe you can put up your logic there. Fine. So the first question is, let a equals to x square, so the 0 less than x less than 1, and b it is going to be square root of x, that is 1 less than x less than 2. Okay, in fact you can just take it not square root of x, just take it more simple way, x cube. Square root I will give that one in another question with few more restriction. Okay, that is x cube. So then the first option, it is there is 1 1 on 2 function between a and b. A is not equivalent with b. Cardinality of a is equal with cardinality of b. A and b are equivalent sets. Very basic question, but it may be MSQ or MCQ type. Okay, fine. Now we are take this first question and solve it. Let me know in the comment section. Now the next question, take it. Question 2, it is, which of the following are equivalent to R? First one 0 1, second one, third one R minus Q, this is intersection, and fourth one R minus Q. Okay, that is also maybe MSQ type of question. And third question, which of the following is or are true? First question or first statement, cardinality of any power set can never be empty. Second option, cardinality of any power set can be empty. Third one, P means power set, P of ... phi, just close the bracket, and 2 to the power n minus 1. Fourth option, power set of a set, is never denumerable. Okay, so this is also maybe MSQ type of question. Try all these 3 questions and let me know in the comment section. Fine. And if you find anything helpful from our videos, then please share it with your friends. So meet you soon in the next video. Thank you for your time.